Alright friends, welcome back. In this video I'd like to go ahead and take a day 2 for section 5.4 from your textbook, and in this video I just want to take a look at a couple of additional examples of exponential equations and logarithmic equations. So let's dive into that. So if you didn't catch the last video, one of the harder questions that we asked in the last video was how do we solve an exponential equation where the bases don't match and they actually aren't related. So we can see here that the bases here are 3 and 7. Those obviously aren't the same number, and 3 and 7 are not related at all. So for this type of equation, remember you're going to have to take a logarithm of both sides and then use that property of logs that allows us to take the exponent and bring it down in front of the log and then trade out those logs of 3 and 7 for the decimal approximations from the calculator. So I'm not going to dive too deep into the rest of the explanation of this problem because that's something that we talked about in the last video, so you can go ahead and check that out if you want to. I want to continue in this video with taking a look at a couple of problems that we have not necessarily seen before, starting with this one, right? So this one looks pretty complicated, right? It looks like we have two different exponentials. We have some minus and plus signs in the mix, and so the question is, how would we go ahead and solve this one? Well, if you were to go ahead and look closely on this, one of the things that you might notice is that this has a familiar form to it. What this is it's something squared in the beginning, something with an exponent that has a 2 in it, minus 3 times that same something, and then plus 2 is equal to 0. And so you can see here that this looks an awful lot like one of those quadratic equations that we used to solve a couple of units ago. And so we know how to solve this, right? So I'm going to leave those blank for now, but we know that if we have a quadratic like this, we can go ahead and always factor it if it factors, and I believe that this one does. So let's factor this into the product of two binomials. We're looking for two numbers that are going to multiply to make positive 2 and add to make negative 3. I think that's going to be negative 1 and negative 2. And then after that, we would split up using zero product property. Now, for these blanks, what I want you to realize is that we don't simply have a single variable, right? Back in the day, if all that was here was x, then we would know how to solve this pretty much immediately. We would just go ahead and set x minus 1 and x minus 2 equal to 0 separately, and then solve from there. But that's not exactly what we had in the very beginning. What we had here was actually an exponential. We had e to the x that goes in these blanks. So it turns out that this is an exponential equation, but it's got a quadratic form to it. And so in these blanks is going to go e to the x, and it's going to perform that same role as that single variable would as we go through, okay? And so this gives us a really easy way to solve the rest of the problem here because we just go ahead and solve it as usual. We're just going to split this up. We're going to say e to the x minus 1 is equal to 0, and e to the x minus 2 is equal to 0. And then we're going to solve these two exponential equations separately. So we're going to add 1 to both sides, add 2 to both sides. That just isolates the exponential for us. So e to the x is equal to 1, and e to the x is equal to 2. Okay, and so this gets it down to a point where we just whittle the equation down to just these two separate exponential equations, and we can see here that the exponential is isolated in both equations. And so according to the last video that we talked about, we can go ahead and convert this over to log language to solve the rest of the problem here. And so e to the we have a log base e, which of course, remember, is a natural log of 1 is equal to x. Okay, if you aren't quite sure what I just did there, then make sure to check out the last video and we'll give you some more explanation there. So natural log of 1, if you were to punch that into the calculator, turns out that that's just 0, and so that just represents our first solution here for this equation. X is equal to 0. If we solve the other exponential here, same thing. We're just going to go ahead and convert to log language. So we're going to start off with a log with a base of e of 2 is equal to x. So log with a base of e is your natural log of 2 is equal to x. And this represents our other solution here for the problem. X is equal to the natural log of 2. And it turns out that that does not equal to something as nice as simply 0 like the first answer was. So we're just going to leave that as a natural log of 2. Okay? And so if you have another problem like this, again, it's a quadratic form type of equation. So you could solve it like a quadratic, but instead of there being a variable here, we have an exponential that plays the role of our variable. And then we just solve it like an exponential there at the very end. In this next example here, this looks a little bit complicated, but I want you to realize that it's actually something that you can do pretty easily by using the calculator. And so if you look at the left-hand side, inside the parentheses, it looks like there's this big confusing expression here. But really, if you look at this thing for a sec, it doesn't involve any variables. These are all values that you know and the calculator knows. And so what that means is that you can just skip straight to the calculator here, and you could just plug this into the calculator and get a nice decimal approximation for it. So let's do that. So 4 minus the fraction we had here, 2.471 over 40. And if we press enter here, we get this nice decimal approximation for what's inside the parentheses there. And so that's going to be 3.938. And so we'll substitute that in. So 3.938, and the numbers keep going. So I'll say dot, 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 all raised to the power of 9t is equal to 21. Okay, and so by trading that out for this nice number right here, we can now go ahead and look at this as an exponential equation, and we can go ahead and solve this by converting it to logarithm language. And so it's going to be the base of our exponential, it's going to be the base of our log, so we're going to say log here of that base number, which is, again, our 3.938 and some change. We're going to go ahead and loop this around to convert this to log language. So log base 3.9 blah, blah, blah of 21 is equal to 9t. Okay, so of 21 is equal to 9t. All right, and so what I now want us to go ahead and do is realize here that the entire left-hand side is something that we can go ahead and punch into the calculator and get a decimal for. And so while I still have that value fresh in the calculator from my previous calculation, I'm going to use that now. So keep in mind to type in a log with any base in the calculator, it's alpha, window, and then the number 5 key to bring up the 5th item in that list. And then because I want the base of this log to be my previous answer, what I can do is just simply use my up arrow button to make sure that my previous answer is highlighted, and then I can just press enter to copy it back down to my line here. And so that copies it down into the base of my log because that's where my cursor was when I arrowed up. And then I could just arrow over to my input where we want to do 21, and then press enter, and we get this nice decimal approximation for what that's going to be equal to. And so we're just going to go ahead and substitute that in the place. We're going to say 2.221 is equal to 9t, and then in order to go ahead and solve the rest of this, we just need to get t isolated. One more step, we just need to go ahead and divide both sides by 9, and we can get a nice decimal approximation for what our value of t is, because again, our values are still fresh in the calculator. So I'm just going to pick up what they divided by 9 and press enter here, and we're going to get this decimal right here. We're going to round to 3 places here, so 0.247 is going to be our final result. Not too shabby. Okay, so this looked like a pretty hard problem to do initially, but if you just keep everything fresh in the calculator as you go through, then it actually turns out to be a pretty easy one to solve, assuming you know what to do with exponential and logarithm equations. So what I want to do here is kind of, take our attention more towards equations that actually have logs in them to start. Okay, and so the very easiest type of log equation to solve is one where you have the same log on both sides. Okay, and so what I mean by the same log is that the logs have the same base on the both sides. So if you have an equation where it's like log base b on the left and log of that same base b on the right, then what you can go ahead and do here is just say that if you want the left-hand side to equal the right-hand side, the only way that that's going to work, since the logs are already the same, is if these inputs are the same. Okay, and so that's what we're going to do to solve the problem, is we're just going to go ahead and set the inputs equal if we notice that the logs are equal on the same side. So let's go ahead and take a look at that. So example 2, part A, we see that that same thing is going on. We're seeing that on the left-hand side, it's just a log base 3. On the right-hand side, it's another log base 3. And so for this, we could just go ahead and set these inputs equal to each other and then solve from there here. So we're going to set the x plus 1 on the left equal to the 2x minus 7 on the right. And again, the way that that is allowed is because it's a log base 3 on both sides. If it was a different base on both sides, we would have to use a different strategy for solving that type of equation. I'm not going to show the rest of the steps here because that's a pretty easy linear equation like you might have seen in a class like Algebra 1. So I'll share with you here that the result is going to simply be 8 and let you work out the rest. Not too bad. For the next equation here, we have a couple of logs, and it looks like they all have the same base because they're all log base e, or the natural log. But it kind of presents a little bit of an interesting dilemma here because we see here on the left-hand side that we're subtracting 2 logs. And that's not quite the case that we had from before. We had a single log on the left and a single log on the right. That was what allowed us to drop those logs. And so we don't have a single log on the left. We have 2 logs that are being subtracted. And so for this, we're going to need to do a little bit of brainstorming. And we're actually going to have to recall back to our lesson 5.3 notes where we talked about these properties of logs that you see right here. Okay, so if you need to go back and watch your 5.3 video, that was the video where we used these properties to go ahead and expand expressions, but we also condensed expressions using these properties. And that's exactly what we're going to have to do here to solve this equation. We're going to have to use that second property, which says that if it is the subtraction between 2 logs, we can condense that down to a single log as long as we do the division of the inputs. So I think the way that we said that back in that video was that if it was a subtraction on the outside like it is here, then that's going to be something that we can condense down to a division on the inside. So we could write a single log, base e, or a natural log, of the division of our inputs here. So that's going to be x plus 1 over x minus 2. It's going to equal the right-hand side. So natural log of x. And that gives us the ability to use that one-to-one property that we just talked about, because now we have the same log on both sides. We can now just go ahead and set these inputs equal to each other. So the one on the left is equal to the one on the right. And when I write down the 1 on the right, since that's simply just x, what I'm going to go ahead and do is write that over 1, because the next step of our work here in order to solve this proportion is to, of course, cross multiply. So if I do that, x plus 1 times 1, I'm just going to get x plus 1. If I do the other cross in the cross multiplication, that's going to be x times x minus 2. And then I could just go ahead and continue to solve this like a quadratic. If I distribute in this x on the right-hand side, I'm going to get x squared minus 2x. And then if I go ahead and simply do some work to bring the x over here, so subtract x from both sides, and then subtract 1 from both sides, then I get the following. I get 0 is equal to x squared minus 3x minus 1. And that's a quadratic formula that we have a lot of different tools in our tool belt for being able to solve. I'm not going to dive into solving this quadratic equation for you here, because this is something that if you were to dive into it deeply here, you would find that it does not factor. Completing the square would be kind of a pain. And so quadratic formula is going to be what you want to go ahead and use here. I'm not going to dive into quadratic formula here in this video because it's not really the focus, but I will share with you that you will get two different answers when you use quadratic formula. You're going to be getting 3 minus the square root of 13 all over 2. And 3 plus the square root of 13 all over 2. And of course, typically we would write that with a plus or minus, but the reason that I'm writing these separately is because we're going to make a point here. Whenever you have a logarithm equation, one of the things that you need to make sure that you remember is that solving an equation means you're finding the number that if you were to plug it into both sides of the equation, you're going to get the same number. The thing about logs is that these machines don't accept all inputs. Logs only accept inputs that are either 0 or some positive number. Logs give you an error if you try to give it an input that's negative, actually. And so if you ever get an answer that's negative here, you might have to check your equation up here for anywhere that you might be plugging into a log all by itself, okay? And we can see up here that if we were trying to plug it in the right-hand side where it just says natural log of x, if we were to try to plug in something negative, then that would actually give us an error in the calculator. And so the negative version of our answer here is actually going to be this first one. So because that's a negative answer, that is actually going to turn out to be an extraneous solution for us. And so we're going to have to throw that out and only accept the other one, because that is not a negative number that we're trying to plug into a log to check our result, okay? So that's going to be one of the quirky things about logarithm equations that we're going to see throughout the video here, is that we're going to really have to make sure that we check our solutions for any ones that happen to be extraneous, okay? So let's take a look at another example of that right here in part C. We see here that we have the sum of two logs on the left-hand side, and so we're going to go ahead and condense that down into a single log by doing the log base 2. Looks like OneNote's not wanting to change my colors there. There we go. So log base 2 of the product of our two inputs. Again, that's our 5.3 video. Feel free to go back and watch that one if you need some more guidance on what I'm doing here in this step. And then, of course, we do have a typo to correct here in this problem here. That should not say log base x. That is a typo. That should say log base 2. Okay. And again, the reason that it's important that we correct that typo is because we couldn't be able to do the problem otherwise, because now we see that if we correct that typo, it's going to be a log base 2 on both sides. We could just simply drop those logs and then continue on with the rest of the problem here. So if we go ahead and do that, distributed property on the left-hand side, and then bring the x and the 6 over, what we're going to end up with here is going to be x plus x, or sorry, x squared plus x, and then minus 6 is equal to 0. Okay? In which case we could factor this up. This is not something that we have to reach for quadratic formula to solve. This is going to be x minus 2 times x plus 3 is equal to 0, in which case we get two solutions. We get x is equal to positive 2 and x is equal to negative 3. Now again, those are two solutions that we got by the natural problem-solving process, but we do have to make sure that if we plug them back into any one of the logarithms in the very original equation, that it's not going to produce something negative. And here I think we're going to have a problem, because we see here on the left-hand side, we're going to have to plug into a log base 2, and that is a negative answer that we got for our x is equal to negative 3. So we're going to have to throw that out. That is our extraneous solution. And we're only going to accept the other solution that we ended up with here, okay? I think OneNote's about to crash here for me, so we're going to have to reopen that here maybe. Possibly. Yep. Sorry about that. Technical difficulty. Let's get that reopened here. Apparently it didn't like something I wrote down, so let's find out. Yes, okay. So yes, we're going to have to go ahead and throw out our negative result. that is extraneous because when we try to plug it back into the original equation, it's going to result in us trying to feed a negative number into a logarithm, which is never allowed. So we're going to only accept our positive solution here as our final answer. Okay, so a couple of different examples of logarithm equations here. I just want to show you two more, and these are going to be the types of log equations where you only have one log in the mix. And so an example like example 3 part A here, if you only have one log in the mix, the way that you'd solve this one is you would convert this over to exponential language and then solve it from there. So a natural log, remember, is just a log with a base of e. And so if I just write that out real quick, this gives us the ability to go ahead and convert this to an exponential equation. Okay, so e to the power of 2 is equal to x. And we can see here that x is pretty much isolated already. So e to the power of 2 is going to be our final answer here. And so if you were to plug that into the calculator, let's go ahead and figure out what that's going to actually be here. So remember that plug in e to the power of, that's second ln. And then we just want to go ahead and do to the power of 2. And then that's going to be 7.389. And that's our final result. Okay, so I'll box the exact answer and then the approximation here as well. If you ever have an equation where the log is not isolated first, that is something you're going to have to go ahead and do here. So I've already done part B just for the sake of time in the video, but you can see here that the steps involved that we're going to have to go ahead and perform 2 steps here, a subtraction of 5 from both sides, and then a division by 2 on both sides to get that log completely isolated. That's what that gray box is for. And then now that we have that isolated, we can go ahead and loop around to change the language into exponential language and then get our answer from there. So that's going to be 2 to the power of negative 1/2, or as a decimal, that's going to be approximately equal to 0.707. The next example that I want to look at is going to be the last example we're going to look at here in this video, and this is just going to be another example where we're going to have to use some of our log properties to help us out here. So we see that we have the sum of 2 logs on the left-hand side, and so we're going to have to condense that down using those properties of logs that we saw from before. So again, that's our 5.3 video if you need to go back and watch that, but we can condense that down to a log base 3 of the product of our 2 inputs, so x times x minus 8. And then that is going to be equal to 2, okay? So now that we've condensed this down to a single log, we only see we have 1 log in the equation. We can go ahead and solve here by converting this over to its exponential version, okay? So we could say 3 to the power of 2 is equal to what we have inside there. So 3 to the power of 2 is equal to x times x minus 8. In which case, we could just go ahead and solve this like a quadratic. So 3 squared is 9. Distributive property says that the right-hand side turns into x squared minus 8x. And then we could bring that 9 over. 0 is equal to x squared minus 8x minus 9. And then continue by factoring here. So if we go ahead and write the 2 binomials here, x and x, I think some combination of 1 and 9 would suit us nicely. How about a negative 9 and a positive 1? That looks pretty good. And we can go ahead and use zero product property to get our 2 solutions. X is equal to negative 1 and x is equal to positive 9. Now again, remember that because we're solving a logarithm equation, we're going to have to check for extraneous solutions, and I think we're going to have a problem here because if we were to try to take this negative result, negative 1, and plug it in upstairs, we're going to have to plug it into a log, and log never accepts negative inputs, and so that is going to be an extraneous solution for this example, and we're only going to accept this positive solution for our logarithm equation here, okay? And so these other examples, part D and part E and F, I invite you to go ahead and pause the screen and read through these here. These would just be examples of what we saw in the previous video, so you can go ahead and convert the language to solve these up, but that's all I have for this video. So again, I just wanted to go ahead and demonstrate how we would solve some of these different new examples here. So if you guys have any questions at all, as always, feel free to let me know, but that's all I have for this one. Thank you very much for your attention, and I will speak to you in the next one.